Hi and welcome to this tutorial on the properties of ionic bonding. So in this tutorial, we're going to have a look at the definitions and remind ourselves what is ionic bonding, what are the structures of ionically bonded compounds, some of their physical properties, and some evidence for the presence of ions. So I'm sure you've seen this before in your prior study of chemistry, but we've got a compound over here. And a compound is formed when two or more elements joined together. So carbon dioxide, we've got carbon and oxygen bonded together, and those are obviously bonded together with a covalent bond. But then we've got ionic bonding. So ionic bonding is the bonding between positively charged and negatively charged ions. So oppositely charged ions due to the electrostatic forces of attraction between those two ions. So normally we'd know that as non-metals and metals. That's what you'd have learned before. And when they are a solid, they form a regular lattice structure like this. And of course, ionic bonding forms as a result of electron transfer. So we've got magnesium oxide here as an example, a metal and a non-metal. And magnesium's got in group 2, so it's got 2 electrons in its outer shell. Oxygen's in group 6, so it's got 6. Oxygen wants to gain 2 rather than lose 6. It's going to gain 2 to get that full octet. And magnesium can lose its 2 and then get bumped down to the shell below, which will again give it that noble gas configuration that it really wants. So then we have MgO forming. So the transfer of electrons between the metal and the non-metal results in the formation of those oppositely charged ions. And they're strongly attracted to each other. So that's electrostatic force of attraction. And the overall charge on an ion has to be 0 of an ionic compound. So, because obviously we can have polyatomic ions, for example, where the overall charge is not 0, but for an ionic compound, it's going to be 0. So NaCl, sodium has lost one of its electrons, it's transferred over to that chlorine. Both have now got their satisfying full outer shell. We're going to show sodium's outer shell as empty. Of course, the shell underneath is full. And it must consist of ions that are completely balanced, as you can see here. And so we've got Na plus and Cl minus. So overall, that is a neutral charge. We can calculate the formula of the ions we've got by comparing the charges of the ions present in the compound. So here we've got sodium chloride. Sodium's in group 1, chlorine's in group 7. That's a +1 and a -1 charge, so it's NaCl. That's going to neutralise those charges. Whereas when we move down to potassium, potassium's a plus. The sulfate polyatomic ion, that's one of the ones you need to learn by heart, is -2. Therefore, we need 2 potassiums, 2 + 1 charges to cancel out that -2. And I'm sure you'll remember from GCSE, well, you might not, but this is often taught, that when we have K plus SO4 2-, we can do that crossing over rule where we pull the numbers down here. Okay, so then we get K2, I'm bringing that 2 over from up here, SO4, and of course I wouldn't write 1, okay, because we never do that. There are different strengths in ionic bonding, so different compounds have different strengths of their lattices. So the strength depends on the ionic charge and the ionic radius. Okay, so the bigger the charge exerted, the greater the attractive forces, the electrostatic forces of attraction between those ions, so the stronger the ionic bond will be. And therefore, with a greater charge, with ions, for example, calcium bonding with carbonate, we've got a greater charge. As their calcium's in group 2, it's a 2+ charge. It's going to have stronger ionic bonding than, for example, sodium chloride, which has only got 1+ and 1- charges. Also, the smaller the ions, the more closely together they're able to pack in the ionic lattice, and therefore the shorter distance between the oppositely charged ions. And that also increases the strength of the electrostatic forces of attraction. And so therefore you get a stronger ionic bond. And there are a few patterns that we need to remember. The ionic radius is going to increase as we go down the group, and it's going to decrease as we go along a period. This is because as we go down the group, we have got an increase in the nuclear charge. We've got an increase in the number of protons, but we've also got an increase in the shielding. And that's going to be a more powerful effect. We're adding more and more electrons, and the outermost electrons are getting further and further away from the nucleus. And so that radius is increasing. So yes, we've got an increase in the nuclear charge, putting those electrons in, but it's offset or it's overwhelmed and it's less relevant. The increase in the shielding is much more powerful. So our radius is going to get bigger and bigger as we add the shells as we go down the group. As we move across the period, we're going to have an increase in the nuclear charge. So the amount of protons is going to increase, but the amount of shielding is not going to change because we're in the same period. So therefore, that increase in the positive charge in the center is going to pull on those outermost electrons more and more strongly as we move across the group. Therefore, the radius is going to decrease, as we move along the period. Therefore, the radius is going to decrease as we move along the period. So looking at the structure, ionic compounds form crystals with a giant ionic lattice structure. So if you can't remember because you're under pressure in the exam, think about salt, sodium chloride. It's crystalline. You know that already. So different ionic compound structures will have different shapes, of course. And the idea of a giant ionic lattice, it doesn't mean it's large. That's not what the word giant means. It means it's infinite, effectively, to say exactly how many ions you have present. Okay, so it just goes on and on into the distance depending on how many you have. And that's what we mean by it consists of endless repeating basic units. So I've got quite a few units here of Na and Cls, but this can go on and on into the distance. I'm just showing you a section of that. So some ionic compounds form giant ionic lattices that will have cube shapes mostly. However, some have slightly different shape structures. And the reason why we have that regular arrangement is because the units or crystals are made of exactly the same repeating units, just sodium and just chlorine. And the physical properties of ionic compounds are determined by their structure. So they've got high melting and boiling points. And the arrangement of their structure within the lattice also dictates whether they can conduct electricity or not. So the melting and boiling points are usually high, of course, because the ions in the giant ionic lattice are held together by those strong electrostatic forces of attraction, which require a lot of energy to overcome. And those electrostatic forces of attraction are in all different directions because it's that giant lattice. And therefore, that's why the high temperature is needed, because of that high amount of energy. The ionic compounds can only conduct electricity when they're dissolved. Okay, or when they're molten as well. So if you heat them up to a high enough temperature such that they actually melt, which is a very high temperature, or if you dissolve them in a solution, then they can conduct electricity. They cannot conduct electricity when they're in their solid crystalline structures. They can conduct them when they're molten or dissolved in a solution because we're going to have mobile charge carriers that are able to carry that charge, okay? So we don't talk about the electrons, we talk about the mobile charge carriers. Check your specification, check the past papers and the mark schemes to see exactly the phrasing you need to use, because it can be really quite fussy with questions like this. And a lot of students will default to say there are delocalized electrons that can carry a charge. And I usually teach OCR. That is not an acceptable answer on that syllabus. You need to talk about mobile charged carriers. So of course, if I was talking about the fact that they can conduct electricity when they're dissolved, they are soluble in water. And again, you know that because if we drop salt into water, it will dissolve. So it means they are, of course, highly soluble, and it's because our water molecules are polar, like dissolves like. So water is polar, it's therefore going to want to dissolve charged ions or other polar molecules. Now, we're talking about ions, so we're not going to talk about them in terms of being polar, but they have got charges on them. So water is going to be able to dissolve them. And they're therefore the water is able to solvate the lattice, so it can break the lattice apart, because these ions would rather be engaging with the water molecules around them than they would in the lattice. Okay, so it's going to break apart because it's energetically favourable for them to be solvated by these water molecules. And you can see how the water molecules have arranged themselves. The red is the oxygen and the white dots are the hydrogens. The positive ions are going to be engaging and attracted to the partially negative oxygen on the water molecule. Remember, if I draw my water molecule out like this, they are polar bonds. So we've got a partially negative charge on the oxygen and partial positives on the hydrogen. So that partially negative is obviously going to be attracted to the positive ions, opposites attract. So that's why the water molecules orientate themselves this way. And in this structure here, you can see the negative ions are going to be attracted to the partially positive hydrogens. So the water molecules are slightly differently orientated. And this is what solvating is. Each of those ions is going to be fully surrounded by water molecules. And therefore the lattice is broken apart. And then we have an experiment that can actually prove that they are soluble in water. So the current theory behind ionic bonding is supported by the physical properties, and we can show the migration of ions when they're dissolved. And we can use electrolysis for this. So when we dissolve it in water, we've got a positive electrode over here and we've got a negative electrode, and the negative dichromate ions migrate towards the positive pole because opposites attract, and the positive copper ions migrate towards the negative pole. Now, copper ions dissolved in water are blue, dichromate ions dissolved in water are orange, and you can see we've got those two colours present. Just a reminder, the negative electrode is also called the cathode and the positive electrode is called the anode.